Hello all. In today's class, we will discuss about time domain specifications. The desired performance characteristics of a control system will be specified in terms of time domain specifications. System with different storage elements will not respond instantaneously, but it will exhibit a different transient response to any input or a disturbance. Okay. The desired performance characteristics of a system of any order, maybe first order or second order, may be specified in terms of transient response to a unit step response of the signal. If we pass a unit step input, it will respond like this. The graph is shown here. The transient response of a system to unit step depends on initial conditions also. It not only depends on the input, it also depends on the initial condition. We usually take zero initial condition for our convenience. Okay, it exhibits damping oscillation before reaching its steady state. It starts with the oscillatory state. Since we have the damping ratio zeta included in the system, it will damp its oscillations and it will reach steady state after a certain time. Okay. So in this graph, if you see, this is a graph plotted between the output C of t with respect to time. It starts with the oscillation and it is damping towards a steady state. Okay, this stage from here to here, it's transient state. After this, it is steady state. Okay. Now in this graph, we have 5 points to discuss. There are 5 characteristics. First one is the delay time, second rise time, third is the peak time, fourth one is your settling time, fifth one is your maximum peak overshoot. What is first delay time? Delay time is nothing but the time taken for the response to reach the 50% of final value. If this is the final value, in our graph 1 is the final value. So time taken for reaching 50% of the final value is your delay time. What is rise time? Time taken for the response to rise from 0 to 100. The time which is taken from 0 to 100. This is your rise time. From here to here, time taken is your rise time. But the time taken for rising varies. This rise time varies for underdamped system, and it is also varying for critically damped system. For underdamped system, we take it for 0 to 100. For critically damped system, we take from 5 to 95%. We don't take 0 to 100. For critically damped, we take from 5 to 95%. Next term is your peak time. It is the time taken for the response to reach the peak value. What is the peak value? Is the maximum value. Okay, maximum value of the graph when it is in oscillatory state. What is the time taken for the response to reach the peak value for the first time? That is called your TP. That is peak time. Then the fourth one is your settling time. What is settling time? It is the time taken for the response to reach within the specified error. If we define the error as 2%, then the time taken for the response to reach the 2% from 0. This is your settling time. If we take it as 5%, then it will vary. Then the last one is your maximum peak overshoot. Maximum peak overshoot is just a formula. It is the ratio of maximum peak value to the final value. When peak value to the final value. Here the final value is 1, the peak value is here. So the difference is MP. Okay. Peak overshoot. Peak overshoot formula, percentage peak overshoot is, I'll show you the formula for peak overshoot. It is nothing but C of TP minus C of infinity divided by C of infinity. And the final value is C of infinity, the peak value is TP. So C of TP minus C of infinity divided by 100. There are formulas for all these things. We have to note down the formulas because we will substitute. Then only we will be able to find the values in the problem. So for the rise time, it is pi minus theta divided by WD. WD is damped oscillation. Pi minus theta divided by WD is your TR. Omega D is, yes, the formula is pi minus 0 divided by WD is for rise time, and it is similar for the peak value. For the peak value, TP is equal to pi divided by WD. In certain problems, theta will not be given directly, so to find the theta, you can use this formula. Theta equal to tan inverse root of 1 minus del square divided by del U. this formula can be used for finding theta. Okay. Now for finding the settling time. Settling time, it is ln of dB divided by L into Wi. For peak overshoot, we have direct formula, which is C into Tp minus C infinity divided by C into 200. These are the formulas used for finding the time response characteristics. Let me dictate our teacher problem right now. What is the problem? The measurement conductor on a servo mechanism shown the system response to be C of t is given. C of t equal to 1 plus 0.25 e power minus 50t minus 1.25 e power minus 10t, and subjected to unit step input, obtain the expression for closed loop transfer function. Determine the undamped natural frequency and damping ratio. Okay. Now, what is asked to find? They are asking you to find WD and the del, Wn and the del. Okay, Wn and del is needed. What is given? Your C of t is given. What is a closed loop transfer function formula? Is C of s divided by R of s. We have C of t. So from C of t, I can find C of s. So apply Laplace transform to the given C of t. The first part becomes 1 by s. The Laplace of e power minus 50t is 1 by s plus a. Here a is 50, so 0.25 is a constant divided by s plus 50. Third term, minus 1.25 is constant. E power minus 10t is 1 divided by s plus a. So this is your C of s. When you solve all these things, taking LCM, we will get this equation with C of s equal to 500 divided by s into s square plus 60s plus 500. Now the s is separate. So 1 by s can be taken separate. That is your unit step input. In the problem itself, it is given the input is unit step input. So 1 by s is taken out so that C of s divided by R of s is equal to 500 divided by s square plus 60s plus 500. Here, comparing this equation with the standard equation, the top omega n square equal to 500. So omega n is equal to root of 500. Which is equal to 22.36 radian per second. Next, if you compare the second term in the denominator, 60 is equal to 2 del omega n. So 2 del omega n equal to 60, from which del can be obtained. Del is equal to 1.3. This is your sample problem. Okay. The next problem is something different, in which we can find the characteristics. Okay, the servo system for a position control system has a closed loop transfer function given as 6 divided by s square plus 2s plus 6. Determine the peak percentage overshoot if the input is sudden move of an equation. Here, we are asking you to find percentage overshoot, I mean MP. MP formula is easy. Percentage MP is equal to e power minus del pi divided by 1 minus del square into 100. Okay, when we compare the given closed transfer function with the standard equation, we can easily find del and omega n. So, comparing this with the standard equation, omega n square equal to 6, so omega n is equal to root of 6. 2 del omega n equal to 2. Substituting omega n here, we will get del equal to 1 by root 6. Okay, substituting del and your substituting del in this MP, you can easily get MP, which is equal to 24.65%. Okay, these are the two problems. Take it as a sample problem. I have given an assignment in the middle. Complete that assignment with reference to these problems. Thank you.